Hello everyone. Today's topic is improbable differential cryptanalysis. So we will move one step away from impossible differential and introduce improbable differential cryptanalysis, which can be seen as the generalization of the impossible cryptanalysis technique. So first we will see the idea behind this cryptanalysis technique, and then we will use this technique on ISO lightweight block cipher standard Clayphia and obtain the best attacks on the cipher that we know so far. So let's start with a brief definition about differential cryptanalysis and its variants. So the basic method, which generally we refer to as classical differential cryptanalysis, was introduced by Biham and Shamir in early 1980s, but we already discussed this before. Most probably a lot of agencies already knew this technique but kept it secret. But first academic announcement of this technique was due to Biham and Shamir. So idea is as follows: you find a path. Sometimes we call it a characteristic or a differential, but in this path we are trying to see some kind of how an input difference affects the output difference. So our aim is to find the input difference alpha that gives some output difference beta with high probability. So our aim is to find a long characteristic, and in this case by long we mean the high number of runs. So higher is better in our sense, so that we can break more rounds of the cipher. So later on in 1994, Knudsen introduced truncated differential cryptanalysis. So idea is the same. You find a path or a differential so that when the input difference is alpha and output difference is beta with high probability. So of course, by me saying high, we mean that the probability should be higher than that event is occurring for a random permutation. So the definitions are the same for differential cryptanalysis and the truncated differential cryptanalysis, but the difference comes from how you define these differences. So in classical differential cryptanalysis, we explicitly write these alpha and beta differences. So saying that if the differences of the bits are 0 or 1. But in truncated differential cryptanalysis, we only specify the parts of these differences and say that other parts can be anything. So this gives us some more freedom. So some ciphers are more resistant to truncated differential and some other are more resistant to differential cryptanalysis. So we cannot say that one of them is better than the other. So it all depends on the design of the cipher. So later on, we talk about impossible differential cryptanalysis. This was introduced by Biham, Birukov, and Shamir in 1998. So idea is to find a path, but this time we call it an impossible differential, so that when the input difference is alpha, the output difference is never beta. So this event, observing the input difference alpha and output difference beta, is impossible. So this event has a probability of occurring 0. So this is somewhat different, and Biham and Birukov and Shamir applied this technique to skip check, which was a cipher designed by NSA, and out of 32 rounds, they could theoretically break 31 rounds. So we speculate that NSA did not know this cryptanalysis technique before the introduction by Biham, Birukov, and Shamir. So there are other differential cryptanalysis variants like higher order differential, boomerang, rectangle attacks, and so on and so forth. But we will move on to improbable differential cryptanalysis, which is somewhat related to impossible differential cryptanalysis. So let's see the idea behind it. So we talked about this before. Statistical attacks on block ciphers make use of a property of the cipher so that an incident characteristic differential occurs with different probabilities depending on whether the correct key is used or not. So initially we actually find a distinguisher, and first we check if this distinguisher occurs with a different probability than a random permutation. Once we obtain such a distinguisher, we add more rounds, and this time we assume that wrong keys act like random permutations, which we call wrong key randomization hypothesis. So the distinguisher we obtain occurs more frequently for the correct key and less frequently for the, for different probabilities for the correct key and the wrong key. But in the traditional attacks, like statistical attacks like differential or truncated differential cryptanalysis, we know that the probability of the incident occurring for a wrong key or a random permutation has some probability p, and it occurs for the cipher, or if it is a key recovery attack, it occurs for the correct key with probability p0. But we know that this p0 is higher than p in differential cryptanalysis or truncated differential cryptanalysis. So generally, this is the case for statistical attacks, but with the introduction of impossible differentials, something different happens. So we obtain a distinguisher, but this time it occurs with some probability p for a random permutation, but it never occurs for that cipher. So it has probability 0. So we know that p0 is 0 this time. So when you look at the difference, in the first scenario, p0 was higher than p, but in this scenario, there is some p, which is non-zero, but p0 is 0. But now the question is, can we obtain something in the middle? So can we have a can we find a distinguisher so that this distinguisher occurs with probability p for a random permutation and p0 for the cipher we are trying to analyze, but p0 is less than p. So the question is, can you find it? Actually, the idea is as follows. If you can find such a distinguisher, of course, you can use it to distinguish the cipher and use it for key recovery attacks, because as we discussed this before, these two scenarios would introduce with these two parameters p and p0, we are actually trying to distinguish two binomial distributions which occur with different probabilities, p and p0. So for the distinguishing scenario, it doesn't matter if the p0 is larger than p or it is less than p. But the question is, so in theory, we can use this kind of distinguishers to attack the cipher. But the question is, how can you obtain such a property? How can you find the distinguisher so that it occurs less frequently for the cipher we are analyzing than a random permutation? So our idea is as follows. So assume that alpha and beta differences are observed with probability p for a wrong key or a random permutation. Obtain a non-trivial differential so that a pair having alpha input difference have beta prime output difference with probability p prime, where beta prime is different than beta. Hence, for the correct key, the probability of observing these differences becomes p times 1 minus p prime. The idea is as follows. Instead of trying to find a path and see which input difference goes to which output difference, your aim is to find a lot of paths which doesn't go to some specified output difference beta, so that you are actually reducing the probability of observing the beta output difference. But you might, there may be also other paths that you cannot see, but which actually goes from alpha to beta with high probability. So if that happens, then this equality might not be correct. So for this kind of attacks, actually you need to perform experiments on the toy version of the distinguisher or the differential so that you can see if it really works or not. So let's discuss how we can obtain this kind of differentials in practice. So I'm going to talk about two methods to obtain improbable differentials. The first one is to use two differentials that miss in the middle with high probability. So we will call it almost miss in the middle technique. So recall that in the impossible differential cryptanalysis, we used a technique called miss in the middle. So idea was to obtain two differentials, like in this case, but in the impossible differentials, these probabilities P1 and P2 were equal to 1. So in the case of impossible differential cryptanalysis, alpha goes to delta with probability of 1 after, for instance, R1 rounds of encryption, and beta has to come from gamma difference after, for instance, R2 rounds of the encryption with probability 1. And if delta is different than gamma, this would give you an impossible differential of R1 plus R2 rounds, saying that alpha never goes to beta output difference after R1 plus R2 rounds. So we are saying that instead of using probability 1 differentials here, make them something very close to 1, so that most probably they will follow this path. So alpha will follow this path, so it will go to delta difference with probability P1, and beta would come from gamma difference with probability P2. So if we assume that these two events are independent, with probability P1 times P2, alpha will not go to beta, so it will go to delta and go to something else. But of course, this means if alpha goes to something else, which happens with 1 minus P1, may also go to beta. So this is why it is not impossible, but it is close to impossible. So this is why we call it improbable. So in this kind of distinguishers we obtain, it is a good idea to perform experiments to see if the independence assumption really works. In some strange cases, for instance, if the runs are really small, if you are attacking small number of runs, and if the diffusion layer is not good for the cipher, this assumption might not work. So it is always a good idea to check the correctness of your distinguisher. So the second technique is the expansion technique. In this case, we expand the impossible differential to improbable differentials by adding a differential to the top or the bottom or both of the impossible differential. So idea is as follows. First, you obtain an impossible differential, most probably using the miss in the middle technique. So you definitely know that delta does not go to gamma. So with probability 1, delta does not go to gamma after some rounds of encryption. For the cipher, you are trying to find this weakness. Now, add a high probability differential to the top so that alpha goes to delta with probability P1. So this means that with probability P1, alpha will go to delta and it will go to something other than gamma. But of course, if alpha does not go to delta, which happens with 1 minus P1, then it is possible for it to go to gamma. So this is why we say that it is not impossible, but improbable. So you can do the same thing. So you can erase this thing and put a differential from bottom and draw the arrow in this direction and obtain an use the expansion technique in that way and obtain an improbable differential. Or you can do both. You can add two differentials, one to the top and one to the bottom. And if, again, with the independence assumption, we assume that these events happen independently, so the probability now becomes P1 times P2. So alpha does not go to beta with probability P1 times P2. So what are the pros and cons of this expansion method? So with this way, you obtain longer differentials, of course, because you are adding more rounds to the top. So for the impossible differential, this was your distinguisher. Now this becomes your distinguisher for the improbable differential. So depending on the number of rounds you are adding to here, you obtain a longer differential. So having longer differentials allows you to attack more rounds most of the time. But of course, this has some drawbacks, because once you move from impossible to improbable using the expansion method, now the data complexity increases because P0 increases. So if we go back to our table, recall that here we are trying to distinguish two binomial distributions where for one of them the probability is P and for the other one it is 0. But for the improbable case, P stays the same, but P0 becomes something larger than 0. So now you have to use more data to distinguish these two binomial distributions, right? So for this reason, data complexity increases in order to distinguish these two distributions in a better way. But once the data complexity increases, time complexity also increases, because you perform this encryption and decryption operations on all of the data you have. So this will increase your time complexity, because you will perform more operations. But also memory complexity increases. Because recall that in the impossible differential cryptanalysis, when you are trying to capture the key, for a guess key, if you observe the impossible differential, this means that that key cannot be the correct one. So you eliminate it. So you can just keep a counter saying which initializes all of the keys to 0, for instance, the counters of these keys to 0. And if you observe the differential for that key, you can make it 1, so that it says that it is not the correct one. So keeping a 1-bit info for all of the guess keys is enough. But now, since it is not impossible, it is improbable, we really need to keep counters like we did in the differential cryptanalysis. But the only difference now is that in the differential attacks, we kept counters for the candidate keys and claimed that the highest counter actually belongs to the correct key. So the exact opposite happens in this scenario. Now the lowest counter should be the correct key, but since we are keeping counters compared to the impossible differential attacks, now we have to use more memory. And before finishing, so let's talk about if there are other techniques or attacks before the discovery of the improbable differential cryptanalysis, so that P0 is less than P. Actually, for the linear cryptanalysis, this is sometimes happens. In the linear cryptanalysis, we have the XOR of the input and output bits of the mask bits, and we check the equality of the XOR of these bits. So an equality is either 0 or 1. So for a random permutation, we claim that this event, that distinguisher, should occur with probability 1/2. And for the cipher or the guess key, it has to occur with some bias, saying namely with probability 1/2 plus Q, where Q is the bias. But if Q is less than 0, because bias can be positive or negative, then it can be an example where P0 is less than P. So in linear cryptanalysis, this is sometimes happens. But other than that, in the literature, before I introduced the improbable differential cryptanalysis technique, I observed 2 papers where people perform some attacks using the fact that the distinguisher they obtain is less probable for a random permutation. So these might be considered as the early examples of improbable differential cryptanalysis.